So we have this set up from the previous video with Betsy, Georgie. I've shown you how Betsy and Georgie end up out here on the heap and that sort of thing. Let me shift F5 here. I want to prove two other things in this video. One, if I instantiate a different type, okay, in this case we had the main class here, which I never got to, but we wrote the code for it in the previous video. So main class, I'm going to instantiate main class, which is pretty empty. Let's do main class in black. So we'll instantiate a main class, and the only thing a main class will have in it is its type object pointer and its sync block index. Alright, and the type object pointer will be a different type, and it's an instance of the exact same type as the cow type object, so maybe I should draw them to be the same size. I'm just kind of running out of room here with my scribbles, but they have exact same types. Right? That's kind of interesting how that goes. These are type instances, TYPE, which is yet just another class inside the .NET framework, but these are both instances of this type object, except this is the main class type object, okay, instance of this type object, and then when I instantiate a main class, its type object pointer will point out to this like so, and its sync block index will be null, and then M is yet another reference on the heap, which is referencing that. So, boy, wow, this is looking like spaghetti, and I hope you're following me. Hopefully you're not too confused at this point. I want to prove that this type object pointer is different for this main class. Then I also want to show you how sync block indices work. So let me get that off the screen, hit F10 again, F10, F10. I need to grab the value of EAX, so debug Windows, registers, Control C that value, 0x, Control V, enter, and we're done with the registers. Scroll up here a little bit. This, well, let me go like this. Let's see, we did Betsy in blue, did we not? So this is Betsy's data right here. Georgie we'll do in black. We haven't instantiated Georgie yet, but I'm willing to bet that the algorithm for finding room on the heap will put Georgie right here again, as we saw in the previous video. And then main class, why did I do Georgie in black? Main class is black. Georgie's red. All right, this is Georgie. Very good. And then main class will only have a type object pointer and a sync block index. And obviously I'm struggling being consistent with my colors. Here's main class's data right there. Watch, let's set move count for Betsy to 9, so that'll change that to a 9. F10, instantiate Georgie, so Georgie will take up this room. We'll see Georgie's type object pointer will be the same as Betsy's type object pointer, which it is. Very good. And then Georgie's move count, I believe, Control scroll. Hopefully you're in high definition. Move count will be 3, which will change this value to a 3. There's our 3. Then we'll instantiate a main class. Here's main class. Notice the address here, though, for main class's type object pointer is different than the one of Georgie and Betsy, and I hope that's what you would expect. And then remember, we got to read these backwards because we're on an Intel processor, so the memory is actually listed backwards. So 4C, or we'll just compare it with this one. 4C, 4C. But then we have 3C, 37. So it's their addresses, if I can get our notepad out here. The address for Betsy and Georgie for their type object pointers are really 4C, 3C, E8. But main class's type object pointer is 4C, 37, 6, 8. So you can see that 4C3, they're close to each other, but they're not identical. So anyway, there we go. I hope this is interesting to you. If it's not, then you've probably stopped watching the video by now. Okay, what about these sync block index? They're null here, null here, null here. Now I don't want to go too much into sync block index. I go into that in great depth in the threading video. Okay, but essentially what Microsoft has done is giving us the sync block index so that we can use any object we instantiate as a mutex, or a way to stop threads from stepping on each other. Again, don't stress what that means if it doesn't make sense. If you're curious, go watch the threading videos. The point I want to stress out to you in this video, and I'm sorry, you're going to have to forgive me up front, because Jamie is a little opinionated about this. But essentially, every object I instantiate, I chew up an extra 4 bytes in RAM for the sync block index. Now, I've been programming a while, and I've been doing .NET for a while, and let me tell you that 99% of the time, I am not locking on an object. Okay, yes, I have to do some threading once in a while, that's true, and I do need to synchronize, so I'll lock, but I'll create one little object, or maybe two, and I'll lock on them. But even though I'm only using 1 or 2 objects to do that, I can create billions of objects of any other type I want to make my program execute, and every single instance of every object I create in my program eats up these 4 bytes for a sync block index. That is insanely stupid. I don't know who at Microsoft came up with the scheme, but the lack of intelligence that went into this planning to waste 4 bytes for every object I create out on the heap so I can lock on it? For real? Duh! Alright, sorry, I'm just... Ooh! Oh, that's... You know, C# and .NET, they got a lot right. They did. They did a good job. But once in a while, you're just like, for real? Oh? And this is one of those things. Another one of those things that drives me nuts is, why did they put get hash code? I'll probably rant about this in a future video not too far from this. But why did they put get hash code in object? If I go here, I type, let me scroll in a little bit here. I think we're done with that. If I type object and I hit F12 on this, and it goes to object, every object gets a get hash code. Every object class you create gets a get hash code. Now, how often are you using get hash code? Get hash code is for when you use an object as a key in a dictionary or a hash table. Now, how often do you do that? How many of your objects are you using as keys in dictionaries? Right? What lack of intelligence went into saying, let's put get hash code in the base class object, even though 99% of the time you will not use it as a key into a dictionary? I think that's just stupid. All right, sorry to get passionate here, but wow. All right, I need to pause the recording and go calm down. I'll be back. Okay, I took a little walk around the block. I'm thinking I'm doing okay. I just, you know, and again, .NET got so much right, but sometimes just like, for real? They should have put this in an interface, and if I want to use something as a key to a dictionary, then I'd just implement that interface. But yeah, all right, I'm soapboxing again. I better not get riled up again. Let me Control S that. So I just want to prove to you that those sync block indexes are what they really are, and what I have to do is lock on an object. So we already know. Well, I'm going to keep Betsy's move count here. We'll get rid of the rest of this, and I'm just going to say lock on Betsy, which is some syntactical sugar for some monitor calls. If you really want to understand what this does, go watch the threading videos. I talk about it in there. But let me let me lock console write line, whatever. Okay. Technically, I really do not need to lock on this code. I'm just trying to do the lock structure to show you that the sync block index bytes will change. So F10, let's instantiate Betsy. Let's go find Betsy. I need debug Windows registers EAX Control C 0x Control V enter. There's Betsy. Oh, I've been looking for you because I'm hungry and I want some steak tonight. All right, this is Betsy's data right here. All right, I told you this is the sync block index. Type object pointer. Very good. Notice the address. I believe that's slightly different from our last run. Moo count, we'll set moo count to 9. We see this value change to 9. Now watch! I am going to lock on Betsy, which does this stuff. Don't stress it too much, but we will see that these 4 bytes take on a whole new value. F10. There you go, our sync block index is 9 into the indices of sync blocks indexes in our process. Go watch the threading videos. But there you go, that's the sync block index. In general, it's a wasted 4 bytes every time you instantiate an object. So, oh well.